Welcome back. We are now moving to section B, which covers core machine learning concepts. These questions build the theoretical foundation on how modern systems learn, generalize, and perform in real-world scenario. In this section, we will discuss feature engineering, which is the creative process of transforming raw variable into meaningful patterns. We will also tackle the critical concepts of overfitting versus generalization and how we use the regularization methods like dropout to prevent our models from memorizing noise. These are the favorite exam topics. So pay close attention to the distinctions between training accuracy and testing accuracy. Welcome back, everyone. In this part, we will cover section B of our internal 2 assessment of data science, which focuses on core machine learning concepts. So these questions build the foundation of how modern ML systems learn, generalize, and perform in a real-world situations. Let's go through each question with clear explanations. So question 11. Transforming raw variables into more informative ones is called future engineering. Sorry, feature engineering. So feature engineering basically refers to the process of transforming raw data into more informative features that a ML model can understand better. So raw inputs like timestamps, text strings, or sensor readings actually don't carry meaningful patterns in when they are in their original form. So by extracting new features such as hours of day, is a weekend, or is a holiday, or any such similar attributes, which by which we allow the model to learn relationship that we previously hidden or which were left to be discovered. And this is one of the most important and creating steps in the machine learning pipeline. 12. Predicting a numeric value such as salary is an example of regression. So when the task involves predicting a continuous numerical value, the problem falls under regression. Examples of regression may include forecasting house prices, salary, temperature, or the sales volume. We can clearly notice that in the following examples which we took here, continuous value are taken in the consideration. Unlike classification, which deals with discrete labels, regression outputs any value along a continuous scale or in an interval. So common regression algorithms include linear regression and support vector regression. Question 13. A model that fits training data perfectly but fails on new data suffers from overfitting. Overfitting occurs when a model learns their training data too precisely. This includes noise and outliers. Such a model performs extremely well on the data which has already seen, or which we call it the training data. But it fails sharply when we expose to the new data other than the training data which it has already been trained. So this is similar to if we take any real life example, like this is similar to someone, a student memorizing answers instead of understanding concepts. So this results in poor generalization and the high variance. Question 14. Dropout and weight penalties are an example of regularization methods. So regularization is a key technique which is used to prevent overfitting. Overfitting, which we just talked about, that the model performs well on the training data, but when new data is found, it doesn't reach its well. So two widely used forms of regression are weight penalties, which we call L1 and L2 regularization, and dropout. So let's talk about weight penalties first. So these add extra penalty terms to the loss function. This encourages the model to keep weight small and simple. Now dropouts. So dropouts are used in neural networks. These temporarily deactivates a random subset of neurons during training. This prevents the network from depending too strongly on any single path and make it more robust. So dropout does what is provides a neural networks a dual path or a multiple path for it to travel. So together these two methods which we just talked is weight personalities, penalties, and dropouts. It helps the model to generalize better to the unseen data so that the both these conditions are used to avoid the overfitting of the data. Coming upon 15, training multiple diverse models to improve accuracy is known as ensemble learning. So ensemble learning combines multiple models to achieve higher accuracy than any single model could achieve alone. Common approaches of the ensemble learning includes bagging and boosting. First one is bagging, which is common of the algorithms of bagging are random forest. So in bagging, multiple models are trained in parallel on different subsets of the data and their predictions are average. So let's talk more on bagging. For example, we have a particular data set. First, we divide the data set into subsequent subsections of the subsets of data, and with each section of our sub data we have suppose we have a data set divided into four parts and we have four models to train. So in this case we will assign each subset to a particular model and will allow it to train, and after training we'll measure the predictions. Each model will predict its own result, and the final prediction will be the average of the all four models which were used to train. Now coming upon boosting, which includes ADA boost or XG boost. In boosting, models are trained sequentially, with each model focusing on correlating the errors of the previous one. So in this case, we can also first we have our data sets. The model passes through the first the data sets passes through the first model. With its learning, it passes to the second model, and in this case, the process goes on. With each passing model, its accuracy is increased here in these cases. So, ensemblers reduce variance and often outperform individual learners. Coming upon 16, a simple reference model for comparison is called a baseline model. So, a baseline model provides a simple reference point that tells how well our advanced model is performing. For example, in a regression problem, a baseline might simply predict the average value for all observations. So if a sophisticated deep learning model doesn't significantly outperform this baseline, then it may not be adding the real value. Coming upon 17, independent unchanging data samples are described as stationary data. So most machine learning algorithms assume that the data sets are I.I.D. That is, each sample is independent from others and all samples come from same probability distribution. So when this assumption breaks, such as in time series data, when where today depends on yesterday, standard algorithms fail. So in these cases, we must use models specifically designed to handle sequential dependencies. Question 18. Parameters tuned before training are called hyperparameters. So hyperparameters are configuration settings chosen before our training begins, training of the models. So these includes learning rate, number of trees in a forest, number of clusters in k-means, and many more such examples are present. So how are these important? So they play a crucial role in the model performance, often requiring tuning through techniques like weight search or a random search. In contrast, model parameters like weights and biases are learned automatically during the training. 19. Comparing two versions statistically to see which performs better is A/B testing. So A/B testing is used to compare two versions of a model to determine which performs better in a real world deployment. The audience or traffic is split into two groups, namely Group A and Group B. Group A is shown to the existing model, whereas Group B is shown to the new model. So, in a performance metrics such as click-through rate, error rate, or accuracy, it is compared statistically. A by B testing is the gold standard for deciding whether to adopt a new model or reject it. Coming up on question number 20. Normalization typically rescales numeric features to a range of closed 0 to 1. So normalization specifically, which is minimum maximum scaling, transform numerical features so that they fall between 0 and 1. So this prevents large scale features from overpowering smaller ones. It is especially important for algorithms that depends on distance calculation, such as k nearest neighbor or the k means. 21. The difference between train and test performed models are variance or overfitting. A large gap between training accuracy and testing accuracy is a sign of high variance, which clearly indicates overfitting of our model. The model performed well on familiar data but struggle with new examples. We want both training data and testing errors to be low and very close to each other. 22. Bias sampling in data collection can cause selection bias. So, selection bias occurs when the collected sample does not represent the population correctly. For example, surveying only wealthy households via telephone in 1984 led to a completely incorrect prediction of the US election results. Selection bias can distort insights and make model unreliable because the training data does not match the real world conditions. So here we successfully completed the section B of our internal assessment of data science. Now in the upcoming videos, we will cover section C and section D. Thank you. So we have successfully wrapped up the section B. We have explored the toolkit of machine learning engineering from ensemble learning to boost accuracy to A by B testing for real world deployment. Crucially, we learned that most algorithms assume that our data is independent and identically distributed, which is I.I.D. And when the assumption breaks, we need specialized models. So don't forget the difference between parameters learned by the model and hyperparameters, which are set by the user. So review these definitions carefully, as understanding the why behind these concepts is key to acing the assessment. Let's move on to the section C, which is deep learning, which we'll be covering in our next video.